Hello again. Welcome to the Linux session of the Antonov AN2 airplane calculation. I prepared the directories and folders with AN2. I can show them. We go to RAID, Antonov, Steady, and here are two folders, Simulation 1 origin body and Simulation 2 15 degrees body of airplane. I go through all necessary steps to generate a mesh. I start this time with cfMesh, meshing of Simulation 1 origin airplane body, because the snappyMesh is already created. When we have prepared the cfMesh, we start the meshing, and as long as cfMesh is calculating, we will look at the snappyMesh. To start the cfMesh, we have to go through all necessary steps. To do this, I open the cfMesh and openFOAM run and look at the commands that we have to execute. We start the cfMesh and openFOAM run. So, first we have to generate a STL combine file in the constant trisurface folder. You see this? We have to go to constant trisurface file. STL combine means that we take all STL files individually in this folder and merge them into a common STL file. For this, I need my Python script STL combine renames files delete text .py. I have already copied it into the target folder, and now I start this script with the typing of following command. I open the terminal and execute the following command: Python STL combine remove files and delete text. Now it's ready, and the result of this execution was created STL combine file. After creating a STL combine file, this one, I convert the STL combine file to FMAS combine file by executing the following command: surface feature STL combine to FMAS combine, and execute this command. The command is not found because the openFOAM is not activated. I forgot to activate the openFOAM. Now I do this and type the following command a new time. So now I have prepared the trisurface folder for cfMesh. In the next step, I switch to the main folder. Let me do it. So I'm in run cfMesh. I go also here to the main folder. Here we are. And now I delete everything that is still left in the folders from the previous meshing. To do that, I go here to cfMesh and openFOAM run and execute the command with remove function. Now we have clean folder, and in the next step I execute the command with cfMesh start with improve mesh quality. So I type the following command and start cfMesh process. Now the cfMesh is running, and as long as it runs, we look at the snappyMesh. I switch to snappy run And first I want to look at the log files. I start with the snappy log. It's written down below. Now I'm interested in the point where the mesh makes a cut. This cut means that the meshing removes all cells what are not in the area of the location in mesh point. We see that the snappy cuts from 56 million cells to 41 million cells. Here is this point where the cut is done, and you see the differences. I open for you snappyHexMesh and show you the place where location in mesh is defined. So castellated mesh control. Here this position. I go back to run snappy, and here also to snappy log. So what is important to me here is how many cells with level 8 we have. This is the level 8, and we have 10 million cells. Level 8 corresponds to a cell size of 2 millimeter. There are almost 10 million cells in total for this refinement level. These are all the cells in the area of cooling grips. I assume that I can mesh the cooling grips in the original thickness of 1 millimeter, although I have analytically predicted too many cells in this case. Too much means that my RAM memory will be overloaded. Anyhow, later I start the meshing where I set the cell size to 1 millimeter in the area of the cooling grips. If this meshing process runs well, then for me it means that I can model the cooling grips in the original thickness on such airplane. What I can also see in the log file is here 13 million cells with refinement level 3. These are the cells from the refinement region, refinement box 3. Let me go to the snappy and show you this refinement object, refinement box, and number 3, and here we see the number of cells in total can be close to 13 million cells. Finally, I can see the time required for the meshing. It is here written below: 12,577 seconds. That means the calculation runs over 3 hours. Next we go to checkmesh log file. So the number of cells is here 41 million cells. I also see 3 failed mesh checks. To see the cells with the bad skewness, I open the paraview. I also close the checkmesh and snappy log files and open the original case. For that I go to media, RAID, Antonov, steady, simulation 1 origin, run snappy, and open the snappy file. First, I want to look at internal mesh. This is written here. I touch apply. Now internal mesh is ready. I can turn it, and I have to make a section and look at the refinement objects. Let me show you the refinement objects. These are all refinement boxes and refinement objects on the airplane section. They looks good. Now I switch to surface of airplane. For that I have to do the following. Now I show only the surface of the airplane. This is the surface of the airplane. I turn off the section. As long as I don't forget, I quickly look at the cells with the bad skewness. For this, I need to go to post-processing, then to constant, and here we see the skew faces. I choose the skew faces and show them as points. I have to select the point and give them the number cell size 20. You see, all cells are in different places. Normally, if the cells are at one boundary, you can change the quality by minimizing of the cell size. In our case, the cells with the bad skewness are located at different boundaries. You see that. Some of them on fuselage, some of them on rudder, some of them on flaps and elevator, as well as on motor fine or motor section. Therefore, the only one way to improve something here is to change the mesh quality settings. For example, my Excel tool is able to export the settings for good or best mesh quality. Now, I do not do this because I think that the calculation can also cope with this mesh quality. Only when the results deviate, I do the settings for a good quality. Another task for us is to check the geometry. I look at all the critical points where the meshing problems could be. For example, we have to look at all places with small distance between two surfaces. These places are where the gap is. There are such places on flaps and wings, for example, on wings bottom. Let me show you. I can create another turn point and turn it around. You see, none of the cells is destroyed. Everything on flaps button is good. Here you see the flaps on top wing. I create another turn point in order to rotate and show you the quality of this mesh. I also see some problems, can be some problems on walls elevator. And now you see there is no problem. None of the cells is destroyed or something like this. Of course, I will also take a look at the cooling creeps. Let me create another turn point. As you can see, we have two or sometimes more than two cells in the rib thickness directory. Cooling creeps looks pretty well. What can I say for this mesh? We are finished with Snappy. The last thing I can do is change the refinement level on the cooling creeps and run Snappy again. I hope the meshing process can finish with this ribs resolution. So for that I go to Snappy. It's already open, and change the resolution. For that I go to walls. Motor fine and change the resolution to 9. I also have to go to the refinement surfaces and change the same. Do the same on walls motor fine here. Now I want to take a look on cfMesh. I open the terminal. cfMesh is still running. As long as it runs, I try to change the color palette on the background of ParaView. I use for the background the gradient. Maybe I take one color green and the second one in the bottom is white. Let me look on this. It's look very good. I let it so, and as long as cfMesh runs to the end, I wait. Now I go to the cfMesh. The meshing is complete, and we start again with log files, or I can directly go to terminal and look on the command line. So let me take a look on checkmesh file. Here we have 38 million cells, so you can see it, which is slightly less than by Snappy. That surprised me a little. So now we go to the quality settings or quality checks. The quality of the mesh has some problems. We have 6 failed mesh checks. Here you see. Even though we use the improve mesh quality options. Nevertheless, I think that the calculation in openFOAM CCM Plus or Fluent will also run under these quality settings. If not, I can't change anything because the settings for the mesh quality in the cfMesh are automatic. At least I don't know how. I don't know the possibility to change the settings for cfMesh quality. If any of you know more about this, please let me know. My contact details are given at the end of this video, or you can simply comment in YouTube. I would like to know where the cells with, for example, bad skewness are located. For this, I go back to ParaView and open the cfMesh. And load the case form to form. Now I go directly to walls of airplane. For that I disable these patches and click apply. Now it's uploaded and I give them the name for this file as cfMesh. So I turn off the snappy and go to surface with edges as well as to solid colors. Then I go to post-processing, or is it Photica face set? Oh, skew faces on okay, we have only skew faces here as a dictionary. I open the skew faces, display the bad skew faces as a dot, points, and enter the size 20 as usual. So now we see bad skew faces. I think they are more placed on flaps. Okay, and also here. Now we can look on the ribs. Here I see the problem for cfMesh. That's why we don't have so much cells as it in Snappy was. So you can see cfMesh is not able to run the mesh with such ribs. That's not good for me. I also want to see some other gaps, places with small gaps. Let me go to flaps of the wing top. Here's everything good. Now I go to horizontal stabilizer and look on elevator. Walls elevator looks also good. So the one problem is the missing of cooling ribs. The cells here are destroyed. In order to do something with the ribs, I have one option. If I increase the refinement level for the ribs, but I have already done this in Snappy, and let me show you the result. The Snappy aborts. You can see MP run notice that process rank 14 with PID 0 on node under PE existed on signal 9 killed. So that the meaning of it is I think we have RAM overload. Here you see 127 million cells, and it was too much. The Snappy file looks the following. So we have here the refinement level on walls motor fine 9, and on refining surfaces also refinement level 9 and 9. So the meshing aborts with these settings. I can try to do the same with cfMesh, but I also think that the RAM memory will be also overloaded. Let me start this. So I go to cfMesh and then to System, Mesh Dict, Motor Fine, on Edge Mesh Refinement and also Surface Mesh Refinement, Walls Motor Fine, number 9. So I hope with this resolution the meshing will be done. We'll be able to finish the process. I also have to copy the run mesh folder in order to I do it twice. So this is the original one. I change the name for this folder with 38 million cells. So, and run the mesh again. So I go to cfMesh, remove all that was created before and start cfMesh again. That's it. Now I have to wait. I have deleted the snappy folder with the cancelled meshing, and also I closed the terminal with this calculation. Now I realize that meshing with more than 130 million hexaeded cells overload the RAM memory of my PC. Too bad, but unfortunately my workstation can not more than 130 million cells. It is also bad thing that there's no way to increase the level of detail of such geometries until the real geometry can be represented and simulated. I hope that cfMesh will calculate the mesh with the new refinement cells. I go to the cfMesh folder, here I want to show the results of the mesh calculation. First I show the cfMesh dict. The resolutions here on the ribs is 9, you can see it, motor walls fine. The resolution on surface mesh and also on edge mesh 9. If we look at the log file, cfMesh log file, we see that the calculation was cancelled due to overload of the PC. Here you see the foam fatal error, negative size requested. cfMesh has also aborted the meshing with higher refinement level on motor fine walls. Now I have the situation where only the snappy was able to create the mesh with refinement level 8 on the ribs during the first simulation. Here is the geometry of Snappy. With the refinements on the cooling grips. You see everything is well. I change the name to Snappy. Now I upload the cfMesh file and show you the bad rips. cfMesh. Here you can see the cfMesh. And especially on the ribs, here we have destroyed cells. I cannot let it stay as it is, and I will take a break and think twice in order to find a solution for cfMesh. Maybe it will be a possibility to me if I change the global cell size and make sure that the cell size on the ribs will be between 1 and 2 millimeters. Now I know that 1 millimeter cell size causes too high number of cells in total, and refinement of 2 millimeters cell size create two cores mesh. For that I have two options. Let me show you a calculation. I delete here everything and do the following. Now we have global cell size 512 millimeter, and the refinement levels are given here below. Here you also see on the left one option to decrease the global cell size, and on the right you have the opportunity to increase that cell size. These are the two options. Either I increase the global cell size up to 768 millimeters and achieve a cell size of 1.5 millimeter at refinement level 9. On the cooling grips, here it is 1.5 millimeters. Or I reduce the global cell size and achieve at cell size of 1.5 millimeter at refinement level 8 on the cooling grips. This is the refinement level 8, and then the other one was the refinement level 9, and this 1.45 millimeter. In the first case, it can happen that cells at the flaps with the small gaps will be destroyed. In the second case, the number of cells may again become too large. I will therefore switch off refinement box 3 to save the cells there. Now I go to cfMesh file. I open the mesh ticket and cfMesh and openFOAM run. Here we see that. Here I will change the max cell size or global cell size to 384 millimeters. I will write origin as 512. Now I also have to decrease or minimize the refinement level on edge mesh refinement, also here on the surfaces to 8. And as I previously already mentioned, I have to comment out the refining box 3 in order to save a little bit cells. So I have to open terminal here. I activate the openFOAM, remove all what is not necessary now, and let run the mesh, cfMesh, with typing of the following command. So we have to wait. After several attempts, I finally managed to achieve a representative mesh in cfMesh. The mesh is ready, only the mesh improvement needs time to come to an end. I also have no access to check mesh and number of cells, but after the log files will be created, we will take a look on it. Now I show you the iteration way. At first, I started with the 512 global cell size and refinement on the ribs by the 8. Then I reduced it to 384 C in green color and let the ribs stay by the refinement level also 8. Then I switched the global cell size to 350, you see it in yellow, and at the end I created the mesh with global cell size 640 and refinement level by cooling ribs by the level 9. That means that cooling ribs have the mesh or cell size on the cooling ribs has 1.25 mm cell size. So you can follow the improvement and the iterations way. Now I show you all examples. This is example with 512 global cell size. You see the cooling ribs are not clear defined and mesh has a lot of destroyed cells. The next step was by 384. You see a little bit more differences. Then I switched to 350 global cell size, and here I see the good result, but I wanted to do it better, and at the end I created the mesh with global cell size 640 and the refinement level by cooling ribs by the level 9. Now I switch to the first calculated snappy file, and you see the cooling ribs are also great. So you can imagine how snappy and cfMesh works in these cases. Let me look on the geometry in total by cfMesh last version. I switch to surface with edges. So I can investigate the first motor section. Everything looks nice. Now I go to flaps on the top wing. Everything looks good. The same situation on flaps in the bottom wing. Okay, everything looks good. Now we see that the mesh will come to an end. I think it is the end of improvement mesh. The next executed command will be check mesh. Now you can see how many RAM memory it takes for the calculation. We have 100 GB RAM memory of 168 GB. Now is check mesh running, and after it goes to an end, we will see how many cells we take in total. So check mesh is running, and the number of cells in this case by cfMesh is 94 million cells. So you can compare it with Snappy, where we have only 41 million cells. I have to point out to everyone that we are generating a highly complex meshes. It is important to mention again that we have divided the geometry of airplane into several small boundaries. All boundaries you can see here. We divided the airplane into several boundaries because we have pursued an optimal number of cells. This means that we set the necessary refinement level on each boundary of the airplane and reduced the number of cells to a minimum. If we had taken the geometry of the airplane as one body, we would calculate too many cells in total, because we would have to take the smallest cell size for the whole body. I am glad that Snappy did a very good job in this case. In my estimation, I could generate a mesh with a cell size of 1.25 mm on the motor cooling surfaces on my computer with Snappy. To do this, I would have to minimize the cells wherever is it possible. In return, I would be able to reproduce the geometry of the airplane with minimal simplifications. In such a case, I could also calculate the thermal process on the engine, for example. However, I will not be pursuing this at the moment due to time constraints. Look at this. We need 160 GB RAM only for check mesh. Check mesh wasn't able to run to an end, and he break here. What I will do soon is to transfer the iteratively obtained settings to mesh calculation 2 with turned wings on the airplane. We export cfMesh dict and run it on the new aircraft geometry. Now I will do it. For that I go to cfMesh folder with 94 million cells. The mesh dict here is the current one, which will be used in the next mesh calculation. I go to run cfMesh and change the mesh dict. Snappy will not be changed because it is now up to date. So what I have to do now, I go to constant folder, try surface, and create a STL combine file. I delete everything and start with origin export here. Then I open terminal and execute the following command: Python stl So we create a general STL combine file. Now I have to go to my cfMesh and openFOAM run script. Go back to constant trisurfaces and activate the openFOAM and do the following. I type the command STL combine to FMS combine. Now it's ready. I show you the FMS combine file is already created. So I go back to the main folder. And now I am ready to run cfMesh. For that I go here and delete at first everything what was created before. Now it's clean. And I can start cfMesh with improved mesh quality as usual. In this example of cfMesh calculation of the airplane with turned wings, you can investigate the checkMesh text. Here is it. Here we have 96 million cells. You see it. And also we have 10 failed mesh checks. It is clear to see how the quality of cfMesh differs from the quality of Snappy, where we had only 3 failed mesh checks. The other point is of course the total number of cells. I would never calculate mesh with 96 million cells if I had the opportunity to use one of it which has 41 million cells. The meshing is now complete. All geometries are good, so the aerodynamic of airplane with turned wings can be also calculated. This geometry shows you snappy mesh. Everything is good here. For example, you can see the cooling ribs and turned wings also. The next geometry I want to show you is cfMesh with simulation 2 and turned wings. Here it is. You see the wings are turned. I can also show you the cooling ribs. Let me show the original case. Here we are. You see 4 or maybe sometimes 5 cells in the thickness direction. This is cfMesh with 94 million cells. As I already mentioned, in the next steps we can calculate the aerodynamic of the airplane. We will be focused on lift and drag forces. Stay with me, it will be very interesting. In order to convert foam mesh to star CD compatible mesh format, I have to execute the following command: foam to star mesh. Let me do it on example. Run Snappy, simulation 1 origin, run Snappy with 41 million cells. The command will be executed in several seconds. The result of such conversion for foam to star mesh you can find in the main folder where the meshing is calculated, and here you can find 3 files with mesh export for foam to star mesh. Of course, it's very simple and easy to convert the foam mesh to Fluent compatible format. For that, I will type in the same directory simulation 1 origin runs snappy with 41 million cells the following command: foam mesh to Fluent. That's it. After a while, you can find the Fluent interface folder in the main directory, and within you can find the MSH file for Ansys Fluent. Now I closed the airplane cases in order to start something new. My last wish is to show you how hexaeder mesh differs from tetraeder mesh. After this experiment, you will realize why hexaeder meshes are advantages. For that, I will open simply case because airplane case is much complicated. And here I will show you the Mercedes-Benz V126 series. For that, I go to this case, I open run mesh only, and I will open the cfMesh. Here I go through meshdict. Let me show you. So you see the edge mesh refinement as it is. Surface mesh refinement has also the basic properties as it was previously defined. I only let refinement box as refinement objects and refinement cylinder for time. So the rest will be as it is. Now I will start it. I open cfMesh and openFOAM run, open the terminal, and as usual start the cfMesh process. I activate openFOAM, remove all what is not needed or what was created before, and start the Cartesian mesh. As long as cfMesh Cartesian mesh run, I will copy the case. Copy. Here I will change the name and write TET-mesh. In this folder we will start the TET-mesh. For that I go and open in terminal. Then I activate the openFOAM here. Now I go to cfMesh and openFOAM run and make a new command line. I copy the old one with Cartesian mesh and change here the Cartesian mesh command to TET-mesh command. Change surface Cartesian mesh, TET-mesh. I rearranged the terminals in screen, and on the left side you can see the result for Cartesian mesh generation for Mercedes-Benz V126 series. On the right side I prepared the place to TET-mesh calculation. In order to run the TET-mesh, I will execute this on the right screen, or on the right terminal. Until it's running, I look on check mesh of Cartesian mesh. We have here about 8 million cells. I will keep it in mind and compare with the TET-mesh cell number. So TET-meshing is done. And you can see here in this folder 92 million cells for cfMesh case. In comparison with Cartesian mesh, we have 10 times more cells with the cfMesh as in Cartesian, or better to say hexaeder mesh. Now imagine for a moment that your computer has to calculate 100 million cells instead of 10 million cells. That is why I tried do not use Tetra mesh. That means that I don't like the workbench mesh generator because it takes most of the time Tetra mesh, and use it in Ansys Fluent. Now I can show you these two meshes, for example Cartesian for Mercedes-Benz and Tetra mesh. So you see, for the same resolution we have approximately 10 times more cells with the cfMesh as it is in Cartesian. So ladies and gentlemen, now it's time to get an overview and formulate a conclusion. First of all, I apologize for having gone through so many iterations until I found a solution. Unfortunately, cfMesh did not play along as well as Snappy. Nevertheless, I think cfMesh did its job. As a result, we have to accept so many cells. Otherwise, we would not be able to use cfMesh for CFD at all. But now you can understand why I work with Snappy in 90% of cases. We have created in total 4 meshes, 2 for each geometry. With these meshes, it is still possible to start the CFD calculation. For the export of the meshes for Fluent or Star CCM+, we can execute known commands. On the one hand, FOAM mesh to Fluent, and on the other hand, FOAM to Star mesh. I think our session has come to an end. For further questions, I am at your disposal. You can find my contact details in the end of this video. I wish everyone all the best. See you in the next video. Bye bye.